Okay, this example is kind of an interesting one. It was motivated by a newspaper article I saw back in 2001. You can see the date here is quite some time ago. And it had to deal with this bomb called a daisy cutter bomb. And there was just this article. The daisy cutter bomb was originally developed in the Vietnam War, and the original intent was to clear out trees for making landing pads for helicopters. So they would drop this bomb. It's a special kind of fuel air sort of bomb that vaporizes fuel and then ignites it, and it creates a big explosion, a huge explosion. And the idea was that it would knock down all the trees, and it would give helicopters a place to land in the jungle in Vietnam. But some military people decided, well, we like big bombs, and so then they decided to use it for other purposes. But anyway, this article was kind of interesting, and I'm gonna just kind of slowly scroll through it. If you want to read the article, you can pause the video and start it slowly, so you can read all that's written here. But what I want to do is get down to the part that is of most interest for this example. Here is the part that I want to show. It's where they're talking about when the bomb explodes. The normal atmospheric pressure is at about 14.7 psi. Actually, they call it 14.2 here. But then they say that when the bomb goes off, the pressure at the center is about 1,000 psi at the center. So, there's a huge change in pressure that occurs. And from that one piece of information, you can actually gather a lot of additional information. And I thought that would be interesting to kind of show you some of the other conditions that are going on just from this one piece of information about the pressure change. And I'll go ahead and just kind of continue to scroll through this so you can see the whole thing. Okay, so that's it. So let's go back to the actual example that I wanted to talk about. This is this one. So we're told that the pressure at the center of this daisy cutter bomb, that the overpressure in the air is approximately 1,000 psi. And from this, by the way, this is what one of these looks like. From this, what we want to do is find the speed of the resulting shock wave, the wind speed following the shock, the temperature after the shock, and the air density after the shock wave. So we're going to use that one piece of information to get the rest of this. So let me just draw a little sketch of what this looks like. So we have this bomb that goes off in the center here, and then it's going to expand. What I've drawn here is like the shock wave, right? And I'm going to call this conditions upstream of the shock wave, conditions 1. These are just normal atmospheric conditions. And after the shock wave has gone by, we'll call that case 2. And so what I'm going to do is just zoom in on a small region of this. So I'm going to zoom in on that so that it looks like this. So we have our shock wave. We're going to treat it as a normal shock wave. And I'm going to change my frame of reference so that instead of standing on the ground, I'm going to stand on the shock wave. So it looks like the shock wave is stationary and that we have flow in and out of the shock wave. So this would be our state 1. This is kind of upstream of the shock wave coming into it. These are our atmospheric conditions. And 2 are the conditions downstream of the shock wave. So that would be kind of back right behind it here. And let me just put some of the variables in here in what we know. So we have V1, Mach number 1. We don't know those values just yet, so I'll put little question marks there. But we do know the pressure there. We'll say it's atmospheric pressure. And just for simplicity, I'm going to call it 15 psia. I won't worry about the 14.7 psia. I'm just going to kind of round it. And I'll say the temperature is 70 degrees Fahrenheit. We're going to leave this in English units. We'd want to convert that over to degrees Rankine, so that's 530 degrees Rankine when you convert it. And the density is just, given that pressure and temperature, you can find the density. That comes out to be 7.7 times 10 to the minus 2 pounds mass per cubic foot. So these are just normal atmospheric conditions. And then when we go through the shock wave, the velocity and Mach number downstream are unknown currently. Temperature, density downstream are unknown. We're going to try to find these. But we do know the pressure. And we'll say that the pressure goes up by a factor of 1,000. So we'll just say it's 1,000 psi plus P atmospheric. So it'll be 1,015 psi A. So it's just, I'm just kind of estimating it here, because the article said that the pressure goes up to 1,000 psi. So I'm just saying that the overpressure, the pressure that it goes up by, is 1,000 psi. So we have 15 psi to start with, just normal atmospheric conditions. But once the shock wave goes by, it's over 1,000 psi. So significant difference. One thing I should note, actually, is as the shock wave expands, it actually gets weaker and weaker. You can imagine that there's a certain amount of energy that's contained within the shock wave. So the explosive goes off, it releases a certain amount of energy. So there's some energy in this normal shock wave, or the spherical shock wave. But then as it propagates out, let's imagine it's propagated out to this far. When it's out that far, all that energy is, it's still contained in the shock wave, but it's spread out over a larger area. Remember, this is like a sphere, so the surface area of the sphere is bigger. So the energy per unit area goes down because it's a bigger surface area. So the shock wave actually gets weaker and weaker as it expands, because the energy is less concentrated. So when we do this analysis here, I assume, based on the article, that it's really when the bomb just goes off, so it's very close to the release point. It's not, 2,000 feet away from where the explosion occurred. And, once you get really far away, the energy per unit area is very small because it has such a large surface area. So the shock wave gets weaker and weaker and weaker. So I'm assuming that these conditions are occurring right when the bomb is released. So it's very close to where the bomb is. Okay. Now, the only information we're really given before and after the shock wave is the pressure, right? So we can form a pressure ratio from that, P2 over P1. So that'd be 1,015 psia all over 15 psia. Make sure you're using absolute pressures. So that's about pressure rise of almost 70. So if you're standing next to this bomb, suddenly the pressure goes up by a factor of 70, which is huge. It's like getting hit with a massive baseball bat all of a sudden. You just have a huge change in pressure all of a sudden. From that pressure change, you can find a whole lot of other information. If you go to the normal shock relations, I'm not going to write out all the equations, but if you go to the normal shock tables, let's say, or the normal shock relations, and you do the calculations, what you'll find is that the upstream Mach number corresponding to that pressure change is 7.7. The downstream Mach number, 0.4. Temperature ratio is 12.5. Density ratio is 5.5. Just some information you can get from those normal shock relations or the normal shock tables. So one of the things that you see right away is, the Mach number of this shock wave is very high. It's 7.7. It's a fast-moving shock wave, right? It's because as the faster the shock wave, the larger the pressure change across the shock wave. And this is a pretty large pressure change, so the Mach number will be pretty large. One thing I just want to highlight here is you see that shock waves are faster than sound waves, right? A sound wave would travel at a Mach number of 1. This is traveling at 7.7 times that speed. So it's shock waves are faster than sound waves. A sound wave is actually an infinitesimally weak shock wave. So, you're not going to outrun the shock wave, right? It's going way too fast. Now, if we want to find the velocity coming in, what we can do is find the temperature, and from the temperature we can get the speed of sound, and from the speed of sound and the Mach number we can get the velocity. So let me just jot that down somewhere here. So to find V1, what we could do is take the Mach number 1 times the speed of sound 1. The speed of sound upstream is just kRT1, right? So we need to find the temperature. Well, but we can we know that temperature T1 actually, it's given right up here, 530 degrees Rankine. So we can calculate the speed of sound. We know the Mach number, so we can find V1. When you work out these numbers, this comes out to be 8,700 feet per second. The shock wave is moving very fast relative to the ground. So that's kind of the speed of the if you're standing on the shock, it's the speed of the air coming into the shock, or if you're standing on the ground, it's the speed of the shock wave going out into the stagnant atmosphere. So it's more than a mile per second, so it definitely is not something you're going to outrun. It's very, very fast. Now, to get the temperature downstream of the shock wave, we can use the temperature ratio. So we know the temperature upstream, it's a balmy 70-degree Fahrenheit day or 530 degrees Rankine. You can see that the temperature behind the shock wave goes up by a factor of 12.5. Huge change in temperature. So, suddenly it gets extremely hot. Now, it doesn't stay at that temperature for an extended period of time. The shock wave moves by very quickly, and a lot of that heat gets radiated away, and there's some conduction away and convection and such. But for a short period of time, it gets extremely hot, and so things can ignite as a result of that. So if you do the calculation of the temperature downstream, it'll come out to be about 6,600 degrees Rankine, which is about 6,100 degrees Fahrenheit, just kind of ballparking it. Huge increase in temperature. So not only can you not outrun it, and you can't, and it feels like you're getting hit with a baseball bat, just a very big, strong baseball bat, the temperature also goes up significantly. The air density will also go up. Here it'll go up by a factor of 5.5. I'm not going to worry about calculating that one for you. It's harder to get kind of a feel for it, but the air density goes up significantly as well. The one last thing I will calculate is the velocity relative to the shock wave downstream of the shock wave. So we'll calculate V2. V2 will be the Mach number 2 times the speed of sound 2. So this is the velocity downstream of the shock relative to the shock wave, and that comes out to be 1,600 feet per second. Now this is the velocity if you're standing on the shock wave. So remember, we're standing on the shock. The V1 is here. V2 is that. It's not the velocity relative to the ground. It's relative to the shock wave. Okay. All right. So we're asked to find, I believe we were asked to find the wind speed following the shock wave. Let's get it relative to the ground as opposed to relative to the wave itself. So to do that, what we need to do is we need to add in the velocity of the shock everywhere. So this is called a Galilean transformation. But basically what we'll do is we'll add in V1 everywhere. We'll add in a V1 to the shock wave, because right in this frame of reference, standing on the shock, it looks like the shock is stationary. What we want to do is get back to the frame of reference of the ground, so we'll add in the velocity V1 everywhere, right? So what happens is upstream, when I add these together, it looks stationary. The shock is now moving at velocity V1 relative to the ground. So upstream, it's stationary relative to the ground. So that makes sense, because what we're trying to do is to get back to where you're standing on the ground and the shock wave is approaching you. So it'll be traveling at velocity V1 approaching you. The velocity up here is about equal to 0. And what we're trying to do is get the V2 here relative to the ground. So what we do is we take this V2 and then we add in the V1, and they're on opposite directions. So to get V2 relative to the ground, it'll be the V1, which is this, and then subtract V2 relative to shock. So this will be, what did we say? We said V1 was 8,700 feet per second. Did I do that right? Yeah. So here's our V1. And then we'll subtract out the 1,600. So this will come out to be 7,100 feet per second. So this is the V behind the shock relative to the ground. So if you're standing there and somehow you've managed to survive the huge and sudden change in pressure, and you've managed to survive the sudden change and huge change in temperature, then you're going to have to contend with this huge velocity of air that is coming past. And it's also going faster than a mile per second. And so yeah, obviously it's just going to blow everything away. This is why all those trees would fall down when the bomb went off, is because there'd be an enormous amount of drag acting on the tree. And because of this super high velocity, and it just basically rips the trees apart. They just fly away. So you can see when this bomb goes off, some really terrible things happen. And oftentimes if you're close to a bomb and it goes off, of course, shrapnel, just the debris that's flying around could, of course, cause damage and kill people, injure them, etc. But not only can the shrapnel cause problems, but the sudden change in pressure and the temperature and velocity can also cause problems as well. And not just to people, but to structures, etc. So anyway, I thought this was kind of a neat example because it shows just from that one piece of information about the increase in pressure across the shock wave gives you so much other additional information. You can get the Mach number of the shock wave, you can get the velocity, if you know the surrounding temperature. You can see how the temperature change, what kind of temperature change you get. You can get the velocity of the wind after the shock wave goes by as well. So it's a lot of information you can get from that one piece of information. So I thought it was a neat example, and it's also pretty incredible some of the numbers that we're dealing with here. These bombs obviously are nothing to be trifled with. Okay, we'll go ahead and end there.